Hi, everybody. Welcome to the new week. Today is going to end our cardiovascular system. We're going to finish off by talking about vessels and circulation. So, your pressure, volume, flow, and resistance are all going to contribute to the way that your blood travels through your arteries and veins. So, when you're looking at the way that blood flows down pressure gradients, it's like we've always talked about with everything beforehand, too. You always travel from areas of high concentration to low concentration. And when you're talking about blood pressure is always going to um, go from highest in the aorta, which is right as soon as it comes out of the heart, right? The blood, as soon as it comes out of the heart, goes into the aorta. And then when you're talking about the size of the arteries, you go aorta is biggest, arteries are middle, arterioles are the smallest. Capillaries are going to be where you exchange the oxygen. So basically, you drop off the oxygen that the arteries carried at the capillary beds. And then now the veins, right? The capillary beds are going to cross over from arteries to veins. The veins are going to be what carry the deoxygenated blood back to the heart. So capillaries then go venules, which are the smallest, veins, which are the middle sized, and then the vena cava, or superior and inferior vena cava more specifically, are going to take the blood directly back into the right atrium of the heart. So blood comes out as highest pressure that you'll ever see. And then pressure is going to fall off as the blood travels through your body and works its way back up to the heart. So blood is going to be at its lowest pressure right before it enters back into the heart. So again, how does blood flow through your cardiovascular system? It's pretty simplistic. Blood is a liquid. Gases flow down pressure gradients from high to low. Your heart is going to create a high pressure during contraction that forces blood into what we call a closed loop of blood vessels, which is going to lower the pressure as it continues. So as blood flows through the system, pressure is going to be lost, as you see here, because of a couple different things. So friction is the major one between the fluid and the blood vessel walls. So as the blood travels through the tubes or your vessels, when it interacts with the vessel walls, the friction is going to slow it down and lose pressure. Pressure drops continuously as you move away from the heart. So then again, one more time, blood has the highest pressure in the aorta and the lowest pressure in the vena cava. This process, when you're talking about pressure, volume, flow, and resistance, is always going to follow the laws of physics. And they can help explain the interactions between pressure, volume, flow, and resistance as they apply to our cardiovascular system. And you'll see in the next unit that these are the same laws that also follow into our respiratory system. Okay, so pressure of a fluid in motion decreases over distance. So what you see here is pressure in a fluid is the force exerted by the fluid on its container. So in this particular example, you've got hydrostatic pressure on the walls of the container from the fluid with inside of the container. Now the hydrostatic pressure in this particular case is going to be proportional to the height of the water column. But once the fluid begins to flow through the system, the pressure is going to drop as you go further and further in distance because of the friction that is going to occur. So the further away you go from this beginning point in what is called these like little spouts, if you will, the lower the pressure is going to be. The best example I can think of for this is, well, if you own a home, hopefully you know what I'm talking about. Drip lines are water systems that we have for like our plants and our gardens and such. And the way that drip lines work is you have one main tube that comes off of like a spout or a water main. And the drip line then is going to be carried through basically plastic over long distances until eventually you cap it off. The pressure of the water that comes out of the first split is going to be higher than the one that comes out of the last split. So if you want to have equal pressure coming out of all of your splits off into like your garden or your flowers or whatever it is you're trying to water, what you really want to do is have the smallest hole to begin with and then have the hole size increasingly get larger and larger to hopefully offset the friction that is lost over distance and the pressure that is lost with it. Um, okay, so pressure in a fluid is, again, the force exerted by the fluid on its container. We commonly measure pressure in millimeters of mercury. So when we, let me just jump back. When we talk about millimeters of mercury, 1 millimeter of mercury is going to equal the pressure of a 1 millimeter high column, so a column like this, of mercury on an area of 1 centimeter squared. So if the fluid is not flowing, the pressure exerted by that fluid is its hydrostatic pressure. And that's going to be exerted equally in all directions, like you see here. Equally in all directions because there's no pressure flowing. So you have pressure that's built up in the same or equal in all columns because of the hydrostatic pressure. When the fluid flows, the pressure changes over distance as the energy is lost due to friction. So although most books will call this pressure in the cardiovascular system hydrostatic pressure, it's actually really called hydraulic pressure, excuse me. Hydraulic pressure, which is the study of fluid in motion, hydraulic pressure. So pressure changes in the liquid without a change in the volume. So what we start to do now is we're going to try to correlate all of these pressure changes because, again, when we talked about last week, all of these numerical values on pressure and stroke volume and heart rate are all really important to look at the functionality of your heart. So what we're going to do today is look at the different factors of flow through your vessels or your vascular system. So again, pressure changes in liquid without changing the volume. So when the size of the container holding the liquid changes, the pressure of the liquid will change. So if you decrease the size of the container, for example, you increase the pressure, while increasing the size of the container is going to decrease the pressure. So they're in an inversely proportional relationship, right? Size of the container goes up, pressure goes down, and opposites. So as the volume of the ventricles decrease, pressure inside of the ventricles is going to increase, and that begins to be our driving force for blood to travel through your blood vessels. So blood vessel changes pressure when you start to dilate or constrict the tubes. So again, dilation is making, so if this is the normal size of the vessel, this would be dilation over here, and this would be constriction over here. So when you change the diameter of the tube, you're going to change the pressure on it just by changing the size, which will then change the volume and change how blood flows through the system. So blood, again, always flows from higher pressure to lower pressure. Blood flow requires a pressure gradient. So flow, again, is going to be directly proportional to any change in pressure. The blood flow requires a pressure gradient. They flow through the tube, and again, it's directly proportional. So as you increase the pressure gradient, you're going to have a greater blood flow. Flow through the tube is going to be dependent upon the pressure gradient and not necessarily the absolute pressure. So when pressure gradients are equal, the flow rates will be equal regardless of the absolute pressure. So here's an example. Fluid flows through the tube, and again, it depends on the pressure gradient. So fluid only flows when there's a positive pressure gradient, meaning there's enough difference to push the fluid from one side to the other. So blood should be traveling from the left to the right over here. And again, it's higher pressure on the right than it is on the left, which is telling the blood what direction to flow. This particular tube has no pressure gradient. So it's 100 millimeters of mercury on the left, 100 millimeters of mercury on the right. There's no big difference in the pressure gradient from one side of the tube to the other, which means there's no pressure change, which means the flow, there is no flow. The theoretical blood in this tube is standing still, which obviously we would know as a problem because we really need our blood to flow. In this next example here, now you're changing the pressure on the left, it's 100 millimeters of mercury, on the right, it's 75. So you have the flow going from left to right. In this particular example, you still have the same differential 25 millimeters of mercury between the left side of the tube and the right side of the tube, but now you have numbers that are different. So instead of 100 millimeters of mercury, you've got 40 millimeters of mercury going to 15 millimeters of mercury. Blood still flows at the same pressure, at the same rate from the left to the right. So we're saying that the flow between these two tubes, while their numerical values are different, the flow is going to be equal because it's talking about the change in pressure, right? So the change in pressure is equal, so the flow will be the same. So again, flow is going to be directly proportional to the change in pressure over resistance. So resistance is a very big component here. So blood flow, we could also say blood flow is going to equal, so BF equals the change in pressure times pi times the resistance to the fourth power divided by 8 times the length times eta. This Greek letter eta stands for viscosity. So this equation to calculate blood flow is called Poiseuille's law. It's a French guy who came up with this equation where we have to factor in a couple of things. So blood flow is going to change when pressure changes, resistance changes, length changes, and viscosity changes. But here's a couple of good things to note. So resistance is going to be the opposition to blood flow and therefore is inversely proportional to blood flow. So for example, if resistance increases, let's go back. If resistance increases, blood flow will decrease. So they're oppositely proportional. So here's your first flow is directly proportional to 1 over resistance, right? So while flow goes up, resistance goes down and vice versa. So there's 3 components that affect the fluid flowing through the tube. Again, radius, the radius of the tube, the length of the tube, the viscosity, which is the Greek letter eta. So the relationship was developed by a French physician named Jean-Leonard Poiseuille, or Jean-Leonard Poiseuille. And again, it tells you that resistance equals 8. I'm sorry. 8L, which is the length, eta divided by it's pi times the radius, So your full equation for blood or flow rate could show something like this. Again, change in pressure, pi, radius, 8 is a constant, length, and viscosity. So you don't have all of these factors changing consistently. So you guys all know that pi is 3.14. You know that 8 here is a constant, but here's a couple other things. When talking a bit about 8ln, we know that the viscosity is going to increase the flow rate viscosity increases, the flow rate decreases. So that has to be on the bottom, right? Inversely proportional. The length of the tube is going to increase, and then the flow rate will decrease. So basically, the longer the tube, the slower the flow rate will be. So that has to be on the bottom. And then you've got your constant. The radius, which is on the top, is going to, when the radius increases, the flow rate will increase as well. So that just goes back to the diameter of the tube. If this is the diameter when vasodilated, and this is the diameter when vasoconstricted, obviously you've got a lot more space, right? Surface area for the blood to travel through. So when you have a larger radius, the flow rate will increase. So if you guys notice, the radius is to the power of 4, which means that the radius is the most important factor when talking about blood flow because it has more weight than anything else, right? You have to multiply it times the power of 4. And then the pressure gradient is going to increase as the flow rate increases as well. So since length and viscosity are relatively constant, right? The length of your tubes should not change. The viscosity of your tubes should not change significantly. Yes, you can, thin your blood with certain medication and stuff like that, but in reality, just with normal physiological environments, the length and the viscosity should stay the same. So your entire bottom denominator is going to be a constant essentially, which tells us that the vessel radius is going to affect the resistance in most of circulation. So since the radius again goes to the power of 4, it's the most dramatic effect with small vessel changes in the radius. Okay, so when talking about resistance in the arterioles, your arterioles are going to be the main site of variability in resistance in the systemic circulation. They contribute about 60% of your total resistance to the flow of the system. You have changes in diameter of the vessels that are affected by local and systemic mechanisms. So you could talk about local control, which matches blood flow to the needs of the tissue. Sympathetic reflexes, which are mediated by your central nervous system, they help maintain your mean arterial pressure and they control blood distribution for your homeostatic needs. So, for example, you can increase or decrease the size of your vessels and help your body temperature regulate. Another factor is hormones. So, specifically those that regulate salt and water excretion, so ADH and aldosterone, those are really influential to blood pressure, which would also help alter your ANS control. So, this particular example shows you as the radius of the tube decreases, like on the left, the resistance to the flow increases. So the volume of we'll call it water in this case, which comes out is much slower than the radius that comes out of the right side because the radius of this vessel or tube, if you will, is much larger. Okay. When we talk about your mean arterial pressure, I don't know if we've specifically said before, but your mean arterial pressure, which again is mediated by your so your sympathetic reflexes get mediated by the CNS. They help maintain your mean arterial pressure to help control homeostatic needs. So how you calculate, so it's mean arterial pressure or MAP, is your diastolic pressure plus 1/3 of your systolic pressure minus your diastolic pressure. Okay, so when talking about myogenic autoregulation, it is what's going to automatically adjust your body's blood flow. So myogenic autoregulation is your body's ability of the smooth muscle in your cardiovascular system to regulate its own state of contraction. So do you need to vasodilate or vasoconstrict? Well, your body automatically knows because of the autoregulation for your myogenic receptors. So, for example, increased pressure on an arteriole increases blood flow through the vessels. When a vessel will stretch, it triggers the automatic constriction to decrease the flow through the vessel. And it works through the stretch receptors that would then cause a depolarization. The depolarization cause an opening of your calcium voltage gated channels. Once they reach threshold, calcium enters, combines with calmodulin, and starts to activate um, the constriction of the vessels. So in this particular example, right, it's showing how blood vessel gets maintained a relatively constant despite an increased blood flow. So your body will automatically trigger the constriction or the dilation that needs to occur based on your body's needs. So we have different chemicals that are going to mediate vasodilation and vasoconstriction of the body. They're produced from multiple sources. So this particular chart shows you the chemical, its physiological role, the source that it comes from, and then the type of chemical messenger that it is. Vasoconstriction is going to decrease the vessel size, which results in increasing your resistance and therefore then would increase your pressure and decrease blood flow. Oppositely, vasodilation increases the size of the vessel, decreases resistance, and then decreases pressure but increases flow. So we've got a couple of different examples that we'll go through here. First one's norepinephrine. Norepinephrine and also a little bit of epinephrine. They are going to be neurotransmitters. that use alpha 1 receptors for tonic control of the arterial diameter in your baroreceptor reflex. So your baroreceptor reflex has to do with body positioning. And the source here is going to be your sympathetic neurons. Next one is, it's not on here, ADH. So some of them aren't on here, but I'll go through ADH as well. ADH is your antidiuretic hormone. It is a neurohormone by type. It's going to work to conserve water in your body, which increases blood pressure and decreases urine output. ANG2 is angiotensin 2. Angiotensin 2 is a hormone. This hormone is produced in the blood. So it's produced in the blood from renin, which is an enzyme that comes from the kidneys to increase your blood pressure. And this source here is a plasma hormone. So ANG2 is something that we'll talk a lot more about when we get to your urinary system, but it is important to know that it does change vasoconstriction, vasodilation because of the increase of blood pressure. Next one is serotonin. Serotonin is a paracrine or a neurotransmitter. It causes smooth muscle contraction, and it works in things like hemostasis or blood clotting, GI contractions to move your food along, and then also with mood and behavior in your CNS. So platelet aggregation, again, that's hemostasis. And then smooth muscle contraction, the only one they forgot here is GI contractions as well. Oh, right here, source. Digestive tract, which would be contractions for your gastrointestinal tract to move your food along your GI tract. Next one's endothelium, which is a paracrine signal. It comes from the endothelial cells or the endothelium, and it controls local blood flow. So just in small concentrated areas. Vasodilation is the opposite side of that. So vasodilation, we'll start here with epinephrine. Epinephrine is a neurohormone. This neurohormone uses beta 2 receptors that are going to increase the flow to organs in your fight or flight response, which is, again, your sympathetic nervous system. So it affects things like your muscles, right? Your muscular system, your heart, and your liver. Next one we'll talk about is your vasoactive intestinal peptide. This is a neurotransmitter or neurohormone. It is going to relax your GI smooth muscle for your digestive system. Relax the smooth muscles. Next one's acetylcholine. This is a common neurotransmitter that we've talked about a lot. It has parasympathetic activity to cause vasodilation by activating nitric oxide. So nitric oxide is a really famous molecular agent because it started off really being used for heart functionality to try to look at how we can better improve our heart function. But when doctors started using this pathway to regulate heart activity, they started noticing that there was a major side effect that they basically rebranded, remarketed, and made themselves millions or billions of dollars because it works for penile erection. So it's indirectly through nitric oxide production. Vasodilation also can, you can talk about specifically nitric oxide as a paracrine signal that comes from the endothelium, and it's going to increase local blood flow. Next one's bradykinin. Bradykinin is a paracrine signal that comes from lots of different tissues. Like when you see inflammation of an individual, it's going to increase blood flow through an increased permeability and has its effects on multiple different types of tissues. Next one is adenosine. Adenosine is a paracrine signal. This paracrine signal is going to be released by hypoxic cells. The hypoxic cells are going to increase flow, and then they're going to match the metabolism rate. Next one is going to be gases. So oxygen, carbon dioxide, hydrogen ions, and potassium. So gases and ions, what happens here is these work as paracrine signals. They are going to change during metabolism because when you eat, obviously these values change, and they lead to active or reactive hyperemia, which then will result in a change in your metabolism. Next one is histamine. Histamine is also a paracrine signal, gets released from mast cells. The histamine is going to increase your blood flow and capillary permeability. So you'll see this a lot with like allergic or inflammatory responses. Next one is your ANP. So it's a natural. So ANP is an atrial natriuretic peptide. It's a hormone or a neurotransmitter that gets specifically released and targets the heart. So, released from the heart, and it's going to increase your sodium loss in the kidneys and then therefore release blood pressure. So, it works opposite of um, aldosterone, antagonistic, if you will. And then again, it targets the myocardium and then sometimes also the brain. And then we've already talked about the vasoactive intestinal peptides. So these are all the chemical mediators for vasodilation. These are all the chemical mediators for vasoconstriction. Make sure you guys know those. So carrying on into the baroreceptor reflex, we touched on this a little bit earlier just with body positioning, and you should have talked about this last semester in the nervous system, but the baroreceptor reflex can also control your blood pressure. So this is a primary pathway for homeostasis of your mean arterial pressure. It's going to be the baroreceptor reflex. So your baroreceptors are mechanoreceptors. So again, they change to mechanical changes. That are located in the walls of the carotids and the aorta, and they help monitor the pressure to the brain and the body. So these receptors are tonic, which means they're continually firing to maintain a normal blood pressure. So when pressure increases, they fire more action potentials. When there's a decrease, then they fire less action potentials. There will be a response to change in the blood pressure that's going to be rapid, and it occurs within 2 heartbeats of the stimulus. So information from your baroreceptors will travel to your cardiovascular system in your medulla, which is then going to either change your cardiac output. So cardiac output would be here, all the way there, or your arterial resistance, your peripheral resistance, or it could affect both, which then in turn would have an effect on your blood pressure. So, for example, when a person is lying down and then stands up, what happens to their baroreceptor response? So, if doing so, some people can get lightheaded. It's a whole physiological response that occurs. Basically, what happens um, when laying down to standing up, your baroreceptor response will call on orthostatic hypotension. That orthostatic hypotension will trigger the baroreceptor reflex. So when you're lying flat in correlation to gravitational forces, they're going to be distributed evenly throughout your body, which means blood is distributed evenly as well. But when you stand up, there's going to be a decrease in the venous return to your heart as blood is going to start to want to pool, P-O-O-L, pool down in your lower extremities just due to gravity. So that would cause a decrease in the venous return and lead to a decreased EDV, or your end diastolic volume, a lower SV, and a lower CO, right, cardiac output. So going from laying down to standing up, so venous return is low, EDV is low, stroke volume is low, CO is low, blood pressure then is low. So you activate the baroreceptor, the sensory neurons, they target the medulla oblongata. That's going to activate your sympathetic nervous system. The sympathetic nervous system will do a couple of things. So when less blood is pumped in circulation, obviously your blood pressure drops, and that's going to be called orthostatic hypotension. Again, one more time, the baroreceptors have to respond to that decreased blood pressure because you might be a little bit lightheaded. You might just start to see those like spots or whatever. Your baroreceptors will send a signal It's a decreased action potential frequency to your cardiovascular control center. So your cardiovascular control center is found in the medulla oblongata. The cardiovascular control center then increases your sympathetic response and decreases the parasympathetic activity, and is going to cause more norepinephrine to be released on the beta 1 receptors of the heart. That's going to cause an increase in heart rate and an increase in CO. You're also going to have more norepinephrine on the beta 1. That's going to cause an increased heart contractility. When you increase heart contractility, that's going to influence the heart rate, which is also going to increase cardiac output. Last one is you're going to have more norepinephrine on the alpha 1 receptors for your arterial smooth muscle, which will increase the vessel size. Increasing of the vessel size will decrease the resistance and increase your total peripheral resistance, which will also increase your blood pressure. The changes in CO and the resistance then all lead toward an increase in blood pressure. Okay, so capillary dynamics. So when talking about capillary dynamics, the distribution of the fluid between the blood plasma and the interstitial space is going to be in the state of dynamic equilibrium. So dynamic equilibrium just means that it's constantly fluctuating with inside its like normal range. Okay, so the distribution of the fluid between the blood plasma and the interstitial space is in the dynamic equilibrium. The movement of the fluid is going to be a result of the hydrostatic pressure. So if the net direction of the fluid movement is into the capillaries, it is absorption. If the net direction of flow is out of the capillaries, that's going to be called filtration, right? Getting rid of it. Most capillaries show a transition of fluid movement from filtration on the arterial side and absorption on the venous side, which means that you're taking the oxygen in to the cells on the venous side, or absorption, and then getting it out of the arterial on the arterial side, filtration. So hydrostatic pressure pushes fluid against the vessel walls, and osmotic pressure is then determined by your solute concentrations, which are going to draw the water towards them. And that's the whole solute suck concept that you should have heard about for the last, I don't know, at least year now. The main solute difference between plasma and IF is the plasma protein albumin, which we talked about previously in blood. That's going to cause osmotic pressure, which we've talked about as colloid osmotic pressure, right? The colloid osmotic pressure in this particular example will show something like 25 millimeters of mercury. And that's the pressure against it. So capillary hydrostatic pressure would look something like this. And it shows about 37 millimeters of mercury. So your interstitial hydrostatic pressure, your interstitial hydrostatic pressure is about 1 millimeter of mercury. So your fluid movement can be calculated by the pressure of the capillaries plus the IF minus the pressure of the interstitial fluid plus the capillary pi of capillaries. So basically what we're saying here is fluid movement is going to be favored out on the arterial side and in on the venous side. That's important, right? Fluid movement is favored out on the arterial side and in on the venous side. Therefore, filtration is going to be greater than the absorption, and therefore an excess fluid in the interstitial spaces can always be returned to the circulatory system through your lymphatic system as well. Lymphatics we'll talk about next week though. Today we're going to end on a little bit of pathology, talking specifically about edema. Edema is a fluid accumulation in the interstitial spaces that we see as swelling. Edema is the result from alterations in your capillary bed exchanges. It can arise from inadequate drainage of your lymph or capillary filtration, and it exceeds absorption. There can be several causes of edema that you'll see here. First one can be obstruction of the um, lymphatic system. So, obstruction of the lymphatic system can be caused by parasites, cancer, fibrous growth that can block your lymph. Elephantitis is a chronic condition that's caused by a filarial worm. Treatment can include it can include basically getting rid of the worm or the infection, which hopefully would stop the further prevention of it and the infestation of it. But this is what elephantitis can look like. Again, this individual has swelling at different limbs due to all of the obstruction of the lymphatic system. Next one could be a cause could be an increase in the capillary hydrostatic pressure. So that would cause an increase in the pressure in the capillaries. Venous obstruction or thrombus would occur that leads to an increase in pressure. That would increase your arterial blood pressure, which causes increased filtration. This could lead to something like the right side of your heart failing. That's going to lead to congestion or heart congestion in the venous system and ultimately would increase your capillary pressure, which would cause greater filtration. This can happen on the left side of the heart, but if it did, it would lead to pulmonary edema. So that really just has to do with where the blood is going after the side of the heart that you're talking about flows to. Next cause would be a decrease in plasma protein concentration. So in this case, you would have a decreased osmosis of the water into the venular ends of the capillary. You could have it leak into localized tissues of edema due to the leakage of the plasma proteins, which could be during inflammation or allergic reactions. It could cause myxedema due to hyperthyroidism. It could lead to severe, or it could be a cause of severe malnutrition, liver failure, or kidney failure. So this is ascites. It's a photo from the 1960s of a Nigerian refugee camp. This individual unfortunately had severe malnutrition and caused edema in his abdominal cavity because of the decreased plasma protein concentration in his body that caused lots of wear on his body. There was insufficient amounts of the albumin and eventually caused liver damage, probably kidney damage as well. Last one here is going to be an increase in interstitial proteins. This is going to be cause a leakage of your plasma proteins into the interstitial spaces from inflammation or allergies, and then again can result in an increased mucin, which results in myxedema from hyperthyroidism. But we've also talked about that previously in the endocrine system, so we won't cover it again here. If you guys have any questions on this, please let me know in the comment section or in email. I'll see you guys next time.